Hello everyone and welcome to a new lecture on discrete mathematics. In today's lecture, we will study graph theory, very important topic in computer science. Graphs are some kind of discrete structures, and in graphs we have some vertices and also we have some degrees. So those edges or points are connected using some links or some edge that we make them like graph. For example, this is a kind of graph. In today's lecture, we will study some basic definition of graphs, different types of graphs, terminologies, representations. Then we will study subgraphs, connectivity in graphs, Hamiltonian and Euler definitions, shortest path problems, planar graphs, and also graph coloring. These are very important topics, and you need to learn them later. In many applications, we use them. The concept of graph theory has been initiated by this gentleman, Euler. So he was a mathematician from Switzerland, and he published one paper in 1736, and this one was somehow a seminal paper in graph theory. So he defined a graph generalization of the simple concept of a set of dots, links, edges, or arcs. So we have some dots which are connected to each other using some links, or you can call them as edges, or you can call them as arcs. How we represent the graph mathematically like this. Graph is equal to G of V and E. In this case, V are vertices, as you can see, A, B, D, C. Also, we call them as nodes. Or edges, this one, this one, this one, this one. These are links or edges. We can use graphs in many different applications like economy, service distribution, marketing, in computer networks, in chemical, for solving many AI problems, we can use them. So here, for example, we have one graph, and this graph has 4 nodes and 5 edges, or 5 links, or 5 channels. Graphs are normally used as a tool to formulate the problems and define a structural relationship. So, for example, you can see here we have many entities, and hierarchically they are, connected to each other. So you can see later we will study trees. Trees also a kind of graphs. So you can see here, for example, like Sejong University as an entity. This Sejong University is connected to some other parent. For example, here we have on the Seoul National University, Yonsei University, KAIST University, Kyunghee University, Inha University, right? In Sejong University, we have like computer science and engineering department, mechanical engineering, chemical engineering, physics. Then in computer science and engineering, we have computer science, AI, we have data science there. Then in here, we have some courses, right? So it's a kind of graphs. To study such problems, we need to study graphs. So we first study some definitions, and later we will learn more about graphs in details. So graphs can have different kind of edge or links. They can be in different types. They are directed. As you can see here, the arrow here is there. If there is one arrow like this, or there is some arrow like this, both sides, then we call them as directed graphs. And in here, order is important. We say ordered pair of vertices. In this case, we have U and V, two nodes, and they are directed from vertex U to vertex V. Directed. It means from V to U, we have no link. Only from U to V, we have link. On the other side, we may have undirected graphs. As you can see here, there is no arrow. It means the relationship between U and V is the same. From U to V is possible, from V to U also possible, right? For example, there are 2 areas, right? There are 2 areas. For example, Nongdong and another area. There is one bus going every day from here to here, but there is no bus from here to here because this bus will go to another place, then another places, then will come here, again come here. So we can say this is a kind of directed graph. This one does not work. We have a bus from this vertex to this one, but we don't have any bus goes from 2 to 1. This is another one because we have many nodes here, right? Then it will not be considered as a link. We call this one as a path, not link. So undirected is unordered, but in this case here both works. And in here UV treats both vertices interchangeably. We also may have a loop, as you can see here. It means from U there is a relation to the U itself. From U to the U itself. So endpoints are in here. We have U and V for one edge, but here the starting and ending is only one node. That's why we call them as loops. And if we have two or more edges joining the same pair of vertices, we call them as multiple edge. For example, if this is one and another one, so we have two, then this way we call them as multiple edge. So graph types, we have many different kind of graphs. So some of them are simple, or we can call them as undirected graphs. In here, if we have a V as a non-empty set of vertices and E as an unordered pair of density, unordered means undirected, right? This is called as unordered. So example here, G, V, and E, how many nodes we have? 1, 2, 3. How many links we have? From U to V, we have one link. From V to W, we have one link. And from U to W, we have one link. So this is a graph. This is a set of vertices. And this is a set of edges, right? That's why this is our graph G. And this is a kind of simple undirected graph. We may have multi-graph. So here you can see that from U to V, we have two edges. From V to W, we have only one edge. That's why we call them as multi-graph, because we have more than one link between a pair of nodes. We call them as parallel edge, also multiple edges. You can call this one as parallel edge or multiple edge. And you can see FE1 is equal to FE2. In this graph, we have three nodes, U, V, and W, and three edges, E1, as you can see here, E2, and E3, three edges. We also have some graphs, which we call them as pseudograph. Pseudograph means similar to graph. So a pseudograph is non-simple. This is simple, it's not simple, as you can see here. This multigraph, it's a multigraph, right? And in here, we have loops. And also we have multiple edges. So as you can see here, we have multiple edge here and we have a loop here. So if our graph has some multiple edge and also there is some loop, then we call this one as a pseudograph. You need to know that trees is a graph that there is no loop or no cycle, right? But in here we have loops. Cycle is different. Cycle is a path. So in here, in this graph, if this is one graph as G, our G is UVW as a node, UVW as a node, E1, E2, E3, and E4 as our edges. So here is our directed graph. So you can see here there are some arrows. From V to W, there is something, but from U to W, there is nothing. This is something later we will study, right? For example, there is a path between two cities. There is a possible flights between two countries, or it can be for, autonomous vehicles where they can find the direction or not, right? So these things later, based on application, we will define them. So directed graphs are kind of ordered paired elements of V, directed edge. For example, here, if this is our graph G, we have U, V, and W as the vertices. We have a link from U to V. See, we have a link from U to V. This is U to V. We have a link from V to W, as you can see. And also we have from W to U. In this case, W and V is not equal to V and W. Because from W to V, we have no link. From V to W, we have a link, but from W to V, we have no link. The same thing for here. WU is okay, but UW is not okay. And in here, we have directed multi-graph, right? So in here, we have, you can see here two links from here, and we have loops also. So one graph with three vertices and four links. Loops we have, and also we have multiple edges. So here is a summary of what we learned so far. We can have simple graph. Simple graphs are undirected. We cannot have multiple edges. We cannot have loops. In multi-graph, also they are undirected. We can have multiple edges, but we cannot have loops. In pseudo-graphs, these are undirected. We can have edge, multiple edge, and also we can have loops. In directed graph, they are directed. We cannot have multiple edge, but we can have loops. In directed multi-graph, directed, we can have multi-edge and we can have loops. So now we want to see some terminologies. Undirected graphs. So if we have U and V as adjacent, we call them adjacent if there is some edge. These two are neighbors. Then adjacent means neighbors. If there is a link between two nodes, we call them adjacent or neighbors. In this case, we call E as incident with U and V, and U and V are called as endpoints. For example, these two nodes are adjacent because there is a link between them, and we call U and V as endpoint, and this link as an incident. We can define degree of vertex. The degree of a vertex is simply the number of edge incident on a special vertex, and we consider a loop as twice. we show them like this, dig V. It means the degree of our vertex V. Dig V. For example, if we have a pendant vertex, then it is 1. In this case, K is considered as isolated vertex because there is no edge from K to any other node. We call them as isolated vertex. But U has a neighbor. W has a neighbor, right? In this case, the degree of U is 2. Why? Because one link is here and another link is here. So the degree of U is 2. The degree of V is 1 because it's connected to only one node. The degree of W is 1 because it is connected to one node. And the degree of K is 0 because it's an isolated node. For directed graphs, if we have edge between U and V, then U is adjacent in the case of directed graphs. So the previous one was for undirected graphs. This one is for directed graphs. So in this case, U is adjacent to V or V is adjacent to U. U is called as initial because the arrow is from this side to this side, right? So a starting point is called as initial vertex, and the V, the destination, is called as terminal vertex. So in here we have two definitions. One is in degree and another one is out degree. In degree, we show it by dig minus U is the number of edges for which is terminal. It means received links, right? Or coming links. So then our U is terminal. It means how many we received, right? Then out degree, or you can say incoming, because it's in, it means incoming. Out means outgoing, or departuring. How many edge is initial vertex? How many we have outgoing? For example, so here the degree of U coming to U is 0 because we have no incoming, but we have two outgoing, two departuring links. So degree plus of U is 2. Degree minus in degree of V is 1 because we have one incoming and one outgoing. So degree plus is 1. For W, the coming is 2, but going is 0. So we have 2 and 0. Here we have one theorem that is called as handshaking theorem. If we have a graph of G of V and E, where V is the node vertices and E is edge, and also it's a kind of undirected graph, and if M is the number of edge, then 2M is equal to the sum of degree of our nodes or vertices. So sum of the degree of our vertices is 2 times of our edge. And incoming and outgoings are equal to the E. It means the sum of this one, the sum of the degree of vertices of a graph is twice of the number of our edge, and in here, the degree of coming and going should be E. In the case of undirected graphs, we have even number of vertices with odd degrees. So, for the proof, if we consider like V1 as the set of even degree vertices and V2 as the odd degree vertices, then 2M is equal to the sum of degree of V, the vertices, which is into V1. V1 is set of vertices with even degree, and here is vertices with odd. So both sum of them, right? And then degree V is even for V in V1. Complete graphs are some kind of special cases in graphs. So if we have Kn as the simple graph that contains exactly one edge between each pair of distinct vertices, so then K1 is this one, K2 is this one. It means from each node we have exactly one edge to another. So if we have K1, it means the number of edges is 0. If 2, so both of them are connected. If 3 are connected. For in computer network, we call this one as mesh topology, right? So from each computer, there is a link to another computer. But a cycle, we show by Cn, and n should be more than 3. It means our graph should have 3 or more number of nodes, right? So consists of n vertices like V1, V2 of Vn. Then there is one link between them, V1, V2, V2, V3, V3, 4, and up to. So here, for C3, there is a cycle. You can see there is a cycle, right? From here, if you start from any node, then you can finally come back to this node. This is called as circle, right? So trees are a kind of graph that there is no circle, because tree is something like this, right? So if you start from here and you cannot go back, and if you come here, then you cannot come here. There is no cycle. Wheels, these are called as wheels, right? So we show them by Wn, obtained by adding additional vertex to Cn. So when we have a cycle and we add one more vertex and connect all vertices to a new vertex by new edge, then we call it as, so this one we call it as a circle. If we add a node here and we connect to all other, then it's kind of wheel. This one you can see here, we have 4 nodes, we added one new, we connected all, then this is wheel, right? And n cubes, we show them by qn, and we represent by 2n bit string of length n. So n cubes are some graphs that we can show them by 2 to the n bit string of length m. For example, this one, we have 2 and 1, right? In here, you can see 1, 0, 1, 1, 0, 0, 0, 1, right? So two vertices are adjacent if and only if the bit string that they represent different by exactly 1 bit. So these two are different in 1 bit. 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 And these two are different in 1 bit. We call them as n cube. N cube. The next thing in graphs that we need to study is bipartite graphs. In here, if V can be partitioned into 2 disjoint sets like V1 and V2 in such a way that every edge in the graph connects a vertex in V1 to V2, right? So if this is V1, V2, V3, V4, V5, V6. So in here, we have a simple graph like G, and we partitioned it into 2 disjoint sets. Disjoint set, it means there is no common, there is no similarity between these two, and every edge in the graph connects one node from V1 to V2, right? So there is no edge in G connects either 2 vertices in one, so there is no connection between the nodes here. There is no connection here. So these connections, we call them as intra-connection. We don't have intra-connection, but these connections are, we call them as interconnection, but we have interconnection. So in these graphs, we have no connection inside the subgraph, but we have connection between corresponding nodes in different subgraphs. Also, we can have complete version of bipartite graphs as well. So if Kn is the graph, its vertex set partitioned into 2, as you can see here, 2 subset of M and N, then there is no edge between 2 vertices if and only if one vertex is in the first subset and the other vertex is another one. As you can see, there is no connection between them, but there is. This is a kind of complete bipartite graphs, these two. There is an edge between 2 vertices if and only if one vertex is in the first subset and the other is in the second subset. This is complete, but in here we may have not to all of them, but in here we have to all of them. From one we have to all, from this one we have to all, right? And subgraphs, in subgraphs we just divide. If this is our main graph G of V and E, then we can have a subgraph of H, V prime, E prime, and V prime is a subset of V. This V is subset of this, and this E prime is a subset of this one, right? So for example, if this is our graph G, then this graph is a subset of this one because we have one less link here, and this one is also a subset of this one because U and V is a subset of U, V, W, and this link also a subset of this one. This is called as subgraphs. So in here we can say that G can be the union of 2 subgraphs. In this case, E, the set of edges, is the union of E1 and E2, as you can see here. So E1 means these edges, right? This is set of edges here, this is set of E2. And V1 is these two, and V2 is these two. So V is the union of V1 and V2. So V1, as you can see, is the U and W. V2 is W and V. And V all here is U, V, and W. In this case, here, edges in G1 is only from U to W, from here W to V, but in here we have 2 links, U to W and V to W. Now we want to learn how to represent a graph, because when we model some problems using graphs, then after that we need to represent them mathematically, and after that we can do coding. There are 2 ways to represent graphs. One is adjacency and one is incidence. So in the case of adjacency, we can go for an adjacency matrix, or we can go for adjacency list. When we want some information about vertices or nodes, we go for adjacency list or matrix. On the other hand, when we are interested to know more about edges, then we go for incident matrix. So these 2 types of representation, incidence and adjacency matrices, are very popular because information about the vertices and edges are important. And if I want to compare which one is more important, adjacency matrix is more important. So here is one example. So we want to go for some adjacency list, and we want to see how to represent a graph using adjacency list. So adjacency list is applicable for the graph that there is no multiple edge. As you can see here, there is only one edge here. We don't have two or more, so we can go for adjacency list. In here, each node has a list of which nodes is adjacent. So for example, we have a node U here, and you can see how many nodes are connected to U, V, and W. In the case of V, we have W and U. In the case of W, we have this one. Very simple. In another example here, for node A, how many neighbors we have for node A? Node B is connected, node C is connected, and node E is connected. In the case of B, only A is connected. In the case of C, A, D, and E connected. In the case of D, C and E, and in the case of E, A, C, D. So this is how we can form adjacency list for a graph. Also, we can use adjacency list for directed graphs. In here, we just list all the vertices that are terminal. Terminal means incoming. So what we do here, in the case of A, B, C, D, E, right? B, C, D. So we have to B, we have to C, we have to D, and we have to E, right? So list the vertices that are terminal vertices of the edges which are initiated from this node. For B, we have to B itself. Here we have a loop. And D, we also have one node to D here, right? We don't have any outgoing. So what we do here, we list outgoing from the node, right? This is the list of outgoing. Then for C, we have one loop here. We have one to A, and also we have one to E. So you can see it. For D, we don't have departure or are incoming, so empty. And in the case of E, we have one to C, one to B, and one to D. So we can see here, very simple. Suppose we have a graph like G, and we have like n as the number of vertices. And if we show our vertices like something like this, V1, V2, V3, up to Vn, the list of nodes, then the adjacency matrix will be a matrix of n to n, right? And in this matrix, we have two values, 1 or 0. We have 1 for Vij if there is an edge between, right? And otherwise, we go for 0. This makes it easier to find subgraphs and also to reverse graphs if we need it. So adjacency is chosen on the ordering of vertices. So here is one example. What we do here, this one is the list of nodes. This is also the list of nodes, right? Then what we do, from V to V, is there any edge or link? No. So V to V means loop. So this one, diagonal, it means if there is a loop, this will be 1. Otherwise, it will be 0. Okay? And then we check. From V to U, there is one link. Okay. From V to W, yes. From U to V, yes. Because this is undirected graph, we consider all. And in this case, we can form our adjacency matrix. Example here, for directed graph. In this case, we say when there is a link between U and V, we consider U to V and U to V, right? So we consider once here and once here only for one link. But in here, direction is important, right? It means this one is V to U, this link is V to U, but it's not U to V, okay? So what we do for adjacency matrix of a directed graph, we look at the arrows. From V to V, there is no loop, so it's 0. From V to U, there is one link, so it's 1. And from V to W, there is no link because the arrow is in this side, so it's 0. From U to V, there is no link, U to U loop, and U to W, yes, we have this link, U to W. W to V, yes, this one. W to U, there is no link, and W to W, no link. So in this way, we can form an adjacency matrix. Another way to present a graph is incidence matrices. In incidence matrix, we normally care about information on edge and we do not consider vertices, right? So for example, if you have a graph, and again, if the list of our vertices is like V1, V2, V3 up to Vn, so this is vertices and edges we have something like E1, E2, up to E of M, right? This is a representation of our graph. Then we can form our incidence matrix with respect to this V and E. So we consider this one as V and this consider as E. And our matrix will be something like M of M, I, and J, right? If there is EJ is connected to VI, we say it's 1. If EJ is not connected to VI, then we call it as 0. If we have multiple edges, then using columns with identical entries, we can consider that because these edges are incident with the same pair of vertices. And in the case of loops, by using a column of exactly one entry equal to 1, we can do it corresponding to vertex that is incident with the loop. So example is here for undirected graph. What do we have here? This one is edges, and this one is vertices. So what we do? V is connected to E1, yes. V is connected to E2, no. V is connected to E3, yes. You can see V is connected to E1 and E3. U is connected to E1, U is connected to E2, but it's not connected to E3 because U is here and E3 is here. W is not connected to E1, it's connected to E2 and it's connected to E3. So in this way, we can form an incident matrix in order to represent a graph. Two graphs have exactly the same form. We call them as isomorphism graph. It means there is one-to-one correspondence between their vertex sets and its. So it's very important to determine whether two graphs are isomorphism or not in graph theory. In such a way, we call them as the two graphs, if they have the same characteristics and attributes, we call them as isomorphic. It means they have similar E and V. Two simple graphs that are not isomorphic, we call them as non-isomorphic. So here is the definition. A and B are adjacent in G1 if and only if FA and FB are adjacent in G2 for all A and B. Example here, if we have G1 as V1, E1, it means V1 is the set of vertices and E1 is the set of edges in graph 1. And also we have G2, which is V2, E2. It means a set of vertices and set of edges, right? In this case, if we have some function, as you can see here, which maps U1 to V1, U2 to V4, U3 to V3. So as you can see here, for example, U1 to V1, U2 to V4, right? U3 to V3, and U4 to V2. It's a kind of function they map. Then we can say this is isomorphism. This function is a kind of one-to-one correspondence between V1 and V2. We can see that these pairs are kind of adjacent vertices in V2. We have several problems that can be modeled using path, maybe for computer networks, maybe for flights, maybe for many schedules, the relation between different entities of the problems. So in order to model such problems, we use graphs. So the basic idea of connectivity is how reachable vertices are by traversing the edge. Or you can say reachability among vertices by traveling the edge. This basic idea is very, very important in many modern problems. For example, in a city-to-city road network, if one city can be reached from another city, right? Or you want to buy a ticket and they want to check whether there is direct flight or multiple flights, how they can offer you the best price, checking the availability of flights between different cities. Or problems if determining whether a message can be sent between two computers using intermediate links in computer networks, right? Or also you can think about efficiently planning routes for data delivery on the internet. In this case, we need to consider path. So far, we talked about link, edge, right? Or channel, sometimes they call it. It means one node to another, right? Neighboring. But now we want to consider more, right? So for example, from V1, V2, V3, V4. In this case, there is no link between V1 and V4. There is no direct link between these two. But there is a path. So a path is a collection of edges. Or you can say a sequence of edges that begin at a vertex of a graph and traverse along edges of the graph, always connecting pairs of adjacent. So this is the meaning of path. How we can represent them if we have a graph of G, V, and E, where V is the set of vertices and E is the set of edges, then you can see here between U and V there is no link, right? But we can form a path. If we come to 1, we come to 4, we come to 5, and we come to V, right? So U1, 1 to 4, 4 to 5, and 5 to V is a path. So U21 is a link or edge, right? But a collection of all is a path. How we can define paths for directed graphs? For example, like n more than 0, from U to V in a graph is a sequence of n edges such that they must be direction. The arrow should be there, right? So we can say that, for example, from E to E1, and in this case, if E1 should be x01, x1, if E2 should be x1, x2, and in this way. Then we can say that a path is traversable, right? We can have like circuit or cycle when you start from somewhere or come to the one, right? When you move in here. And simple path means we do not have any repeated edge. It means we traverse a graph, but we do not pass a vertex 2 times. Does not contain any edge more than once. It means one path only one time traversing. In the case of undirected graphs, so we say that undirected graph is connected if there exists a simple path between every pair of vertices. And example is here, we say this one is connected. Okay, now how we can say that this graph, undirected graph, is connected or not, right? Connected. It means there should be one path, simple path. Simple path means you cannot do like this, then come back here. It's wrong, right? Simple path means one edge, one time. So if I want to go from V1 to V2 available, V3 available, V4 available, V5 available. That's why this is a connected graph. The same, V5 to V4 available, to here available, to here available, and to here available. So we call this one as a connected graph. Because between any pair of vertices, we can find a simple path. Simple path. Here we have a topic of articulation point, or we call it as cut vertex as well. If we remove a vertex, then it produces a subgraph with more connected component than its original one. So in here, our main objective is to select a node, and then we remove the node. Then we have some subgraphs, and in our subgraphs, the connectivity is more than the original, right? The removal of cut vertex from connected graph produces a graph that is not connected. When we say cut vertex, we consider one node to be removed, and in cut edge, we consider one edge to remove. So if we have an edge and if we remove it, then we have some subgraphs that they are more connected compared to before removing of that edge. So example is here. This graph is the, we have this V3, and this V3 is called as articulation point, or this edge of V2 to V3, this one is called as, so we call this one as cut vertex, and this one we call it as cut edge. So if you remove them, then we have two graphs which are more connected, right? More connected. Strongly connected directed graphs. We can say a directed graph is strongly connected if there is a path from A to B, and also from B to A. So it means the corresponding one to another must be available vice versa. On the other hand, we call a directed graph as weak if there is undirected path between every two vertices in the underlying undirected path. So here some example to see a strong connected and weak connected. So here in G1 is a strong connected because from anyone we can go to any other, right? But this is weak because from this one we cannot come here. From here we can come to here. From here we can come to here. From here we cannot go to this A, right? If this is A, B, C. So A to B is available, but B to A is not available. A to C is available, but C to A is not available, right? And if you want to go for undirected, then this one is somehow representation of these two in case of undirected. Directed graphs, we have a strongly connected component also, and you can see that we can, if this is our graph G, we can make a subgraph of G that is strongly connected. This one is not strongly connected, but we can make subgraph of strong. By removing this one and make it as a subgraph, then you can see this is strongly connected. The next topic is isomorphic invariant. An isomorphic invariant for simple graph is simply the existence of a simple circuit or cycle of length k more than 2, right? So we can see here we have G1 and G2. These G1 and G2 are isomorphic because we have the invariance, similarity in edge on nodes, and the number of edge and number of nodes and length of circuit is the same. So we call them as isomorphic invariants. How we can count the number of paths in a graph? So if we have like graph is G and A is the matrix of availability of links and vertices, right? As you can see here, this is A to A is not available, A to B is available, A to C is available, A to D not available, right? B to A available, B to B not available, B to C not available, B to D. So this is representation of this one, right? So now I want to find out the number of paths, right? The number of different paths with the length of R, from Vi to Vj, it means any vertices in our graph, is equal to A to the R. What we do here, R is the number of paths. For example, we have a graph and I want to find a path of 5 lengths, right? It means my path is included 5 links, 5 edges, right? What we do, I make it A to the 5, then I go to the ijth entry of this matrix and find the number. So again, I want to find the number of R length. R length means a path which consists of R edges, right? What I do, I just multiply the matrix R times and I find the ijth representation. For example, here, in this example, how many paths of length 4 is available from A to D? A to D, right? So one is like this, maybe, like this, right? So what I do here, this is the matrix. So if you do A multiply A multiply A multiply A, then you will have this matrix, right? Then if this is A, B, C, D, A, B, C, D, and I want to find ij to j, right? Then A to D is 8. There are 8 possible paths of length 4 between A and 1 is, for example, A to B, BA, B, D. This is 1, right? Because we are looking for the length of 4. It must be 4, right? Another one is A, B, A, C, D, right? Another one is A, B, D, B, D, right? A, B, D, C, D. There are 8 possible ways to find a path of length 4 between A and D. And the same thing you can go for others. This graph theory, in fact, started from a problem long time ago, maybe in 1736. And there was one city. The name of the city was Königsberg. That time was in Germany, but I think now it's in Russia. And they call this problem as Seven Bridges of Königsberg, and it's a kind of historical notable problem in mathematics. And this is a very good example for graph theory. The problem was, we have a city, like this is a city, and there are 7 bridges, 1, 2, 3, 4, 5, 6, 7, right? The mayor of the city says, in Sunday, if some citizen of this city wake up and he wants to, hang out with friends in the city, and can they go every morning from one place, for example, from here, and they go for all different parts of the city. But the problem is to go only once. If we can walk through the city, that would cross each of those 7 bridges exactly once. Later, in 1736, one Swiss mathematician, Leonhard Euler, as I already introduced to you, he said no. The simple question was no. This was the starting point of the graph theory. So what he did, he converted this problem into graph, as you can see here, and he pointed each place as a point and each bridge as an edge, right? Then how we can go and just by only one time and come back to your home. This is the problem. So here is an important question that we should find a solution for it. Can we travel along edges of a graph, starting a vertex and returning to it by traversing each edge of the graph exactly once? This is a problem. Another problem is, can we travel along the edges of graph, starting at a vertex and returning to it while visiting each vertex exactly once? These two questions are somehow similar, but in fact they are different. Two concepts we should learn to ask this question. One is Euler circuit and Hamilton circuit. So in Euler circuit, edges are important. In Hamilton, vertex are important. So we say Eulerian path, or you can say Eulerian trial, and also it called as Euler walk. In a graph is a path that uses each edge only once. Edge only once. This is the condition. If such Eulerian path exists, then we can say this graph is traversable. Then we have a cycle. Cycle means you start from one point and come back to the one point. So in a graph, we can say that one cycle is Eulerian circle or cycle or circuit that uses each edge precisely once. So path means from one point to another point. So these V1 and V2 can be different, but circuit means come back to here while you passes many other vertices. So here, for example, if you want to travel all the edges, here edges are important, not points. For example, A to C to D to E to B to D to A to B. So every edge was traveled once, not vertex. Here in Euler, only edge is important, and we care that to not pass a edge twice, not a vertex. For a shape to be traversable, we have to care that all vertices are even degree. If all vertices are even degree, or exactly two vertices are of odd order and the rest are even, then we say this shape or this graph is traversable. For example, in this shape, we have two odd and two even. What are odd? For example, C, 1, 2, 3, right? And D, 1, 2, 3. So C and D are odd. A, 1, 2, 3, 4, 5, 6, and B, 1, 2, 3, 4. So even. That's why we have two vertices odd and even. Oh, say this is traversable. How about this one? All are even. All are even. That's why this is also traversable. How about our graph that we have just made for the problem of Seven Bridges of Königsberg? In here, if you draw like this, A is odd. Why? Because 1, 2, 3, 4, 5. So A is odd. B is odd. 1, 2, 3. D is odd. 1, 2, 3. And C is odd. 1, 2, 3. Right? So we have 4 odd nodes and 0 even. Because we learned that there are two ways that a graph is traversable. All verticals are even, and exactly two vertices are odd on other ones. Because this problem does not satisfy two conditions, so this is not traversable. As I said, Leonhard Euler, he proved this one, the fact, he proved this fact, and because of this fact said it is not possible. But it was the starting point of graph theory. So here is what we say that it's not possible, but somehow you can go like this if you ignore these two. Eulerian graph, if you have a connected graph like G, is Eulerian if and only if this graph is connected, one condition, and has no vertices of odd. So, and then a connected graph is an Eulerian trial if and only if the graph is connected and A to B are the only two nodes of eventy. So these two conditions we check to see whether a graph is Eulerian graph or Eulerian trial. For example, if we have a graph of Euler trial and we have from node A to B and A and B are not distinct, then for every node beside A and B, T uses an edge to exit. For each edge, it uses to enter. For example, in here, the degree of the node is even. So if A is equal to B, then A also has even degree, then we call it as Euler circle. And if it's not, A is not equal to B, A and B both have odd degree, and then it's a Eulerian path. Euler graph. If we have a connected graph, we call it as Eulerian if and only if the graph is connected and has no vertices of odd degree. For example, in here, we building a simple path, A to B, this one, B to C, then C to F, and F to A. So this is the Eulerian circuit constructed. In the second part, for this part, we delete the simple path, A, B, C, A to B, and BC2, and we delete the all is common vertex for this subgraph as the parent. Then we merge them, right? So once we apply for this part, then we apply for this part, then we go here and we splice the circuit in the second graph, right? So A to B, B to C, C to F, F to A, this one, and then from C to D, D to E, E to C1, then fully we have 1. When we have some complex graph, we apply this separation and apply, then combine all together. How to make a Euler circuit? Here is the procedure. We know that Euler circuit is a circuit that uses every edge in a graph with no repeats. Being a circuit, it must start and end at the same vertex. A graph will contain a Euler path if it contains at most 2 vertices of odd degree, and a graph contains a Euler circuit if all vertices have even degree. If you have a graph like G and it's a connected multi-graph with all vertices of even degree, this is the condition, then circuit is a circuit with G beginning at any arbitrary chosen vertex with A successively added to that return to this vertex. So circuit means going and come back to itself. Then we have H, the edges of the circuit removed, so somehow subgraph. Then we go to the edge in order to make something like this. We will go to the edge, as H is a subgraph. So subcircuit a circuit in H beginning at vertex in H that also is an endpoint of the edge. Then we update H with edges with subcircuit and all isolated vertices removed. Then we made this our circuit and we will return our circuit back. So here we can see the incidence matrix as well. So we have nodes A, B, C, D, E, and F, as you can see here. Our nodes and how many edges we have: E1, E2, E3, E4, E5, E6, E7. You can see here. Incidence matrix means whether a node is connected to an edge or not. A to E1, yes. E2, no, only E7. To B, we have E1 and E2. Let's do 0. To C, we have E2 and E3. To D, we have E3 and E4. To E, we have E4 and E5. To F, we have. So this is how we form our incidence matrix. So now I want to talk about Hamilton paths. So in here, vertex is important. In Eulerian, it's very important. Hamilton path, also called as traceable path, is simply a path that visits each vertex exactly once. Then, similarly, we have Hamilton cycle or Hamilton circuit. It's a cycle that visits each vertex exactly once. Path means starting from edge, one edge, and go to another edge, not the same. In here, coming back to them. And in the circuit, every vertex should be visited only once, except the starting point, because once we go and once we come, it's okay. This starting point is okay. So a graph that contains a Hamilton path, we call it as a traceable graph. A graph that contains a Hamilton cycle, also we call it as a Hamilton graph. So any Hamilton cycle can be converted to a Hamilton path by removing one edge, right? So if you have this circle, right, and if you remove one edge, then it becomes a path. So here we have a graph of the vertices of the dodecahedron. This means 12 sides. This means 12 sides. So how we can travel this one based on Hamilton to go only once, right? How we can do it? Like this. If we start from here and come into here, then we can say this is a Hamilton graph because we visited every node only once. This one has an Euler tour but no Hamilton path because we can traverse the graph by passing all edges once. If I do like this, as you can see, in this way, I visited every edge once, so it's Euler. But is it Hamilton? No, because this point has been visited 2 times, so it's not Hamilton. Because this point was visited 2 times. If I start from the node itself, if I start from here, this is Hamilton or not? Still not, because this node had been visited 3 times. 1 time here, starting, then I come here, 2nd time, then 3rd time. It's not accepted. How about if I start here? If I start here, again, not possible, right? If I start from here, not. So this is not Hamilton, but it's Euler. Similar notion may be defined for directed graphs where our edges of a graph or cycles are required to point in the same direction, like connected tail to head. The Hamilton cycle problem, or also known as Hamilton circle problem, in graph theory, our intention is to find a Hamilton cycle in any graph. So if we have a graph, how we can find a Hamilton cycle? And you remember that Hamilton cycle means we start from one node, we travel all the other nodes, and we come back to the same node. In here, edges are not important. It means you can travel the edge as you want. The Hamilton path problem will help us how to do it. There is a simple relation between these two, and we want to find out this using these theorems. The Hamilton path problem for a graph is equivalent to Hamilton cycle in another graph, and another graph means we somehow drift from our main graph. How? By adding a new vertex and connecting it to all the other vertices. So these problems are considered as NP complete. NP complete means non-deterministic polynomial time complete, and it means there is no single efficient solution for this problem. However, certain classes of graphs always contain Hamilton paths. For example, it is known that every tournament has an odd number of Hamilton paths. So 2 theorems are here. One is Dirac's theorem and Ore's theorem. If you have a graph like G, and this is a simple graph, not multi-graph, and n is more than 3, number of vertices is more than 3 or more, such that the degree of every vertex G is at least n by 2, then G is a Hamilton. So if you have a graph, the number of vertices is 3 or more, and the degree of every one is, can say 3 by 2. If it is 4, it means 2 or more, then it is a Hamilton circle. And another theorem says if you have a graph again, n equal to more than 3, and the degree of u and degree of v is more than n for every pair of non-adjoint sets u and v nodes in our graph, then it's a kind of Hamilton graph. These two theorems will help us to simply find out whether Hamilton circuit is there or not. Why? Because for all the problems, like for example, you want to navigate from some point to another point, and the navigation system is not going to draw lines like this, right? So normally they employ these two theorems, and these theorems will help the navigation system to find the best possible path or circle for you. Now we learned the basics of graphs. We want to go for some problems which are known as the shortest path problem. In many applications, our objective is to find the shortest possible path because they can be modeled using graphs with weights assigned to their edges. Consider how an airline system can be modeled. We set up the basic graph model by representing cities by vertices and flights by edges. Then we want to find out the flights between different cities with the shortest path. So in here, we want to find the path with shortest weight. So our goal is to generalize distance to weight setting. If we have a graph like this one, and this is a directed graph, like graph, and this is our weights, assigning real value to it, for example. Then weight of path, for example, if you have a path of, for example, like this, P is equal to V1, V2, V3, up to Vk, then the path I from 1 to K1 is weight multiply the edges, right? It means if you start from here, right, weight of this one plus weight of this one plus weight of that, right? This is how we can do that. And this one, whether it gives us whether there is a path available between them or not, 0. Shortest path is a path of minimum weights. This has many applications. In AI, we use this algorithm. It can be used for static and dynamic network routing, robot motion planning, map or road generation in traffic, and many other things. So shortest path problems, normally single source or single destination, we want to find the shortest path from a given source like vertex X to each of the other vertices. And in single pair, if we have two vertices, our goal is to find the shortest path between them. Solution to single source problem, solve the problem efficiency also. And all pairs in here, so in this case, we want to find the shortest path for every vertices. And in this case, maybe we go for dynamic programming. And the last one is unweighted shortest path. It means we want to find the shortest path regardless of the weights. These are the four main possible categories or cases that we may have in different applications where the problem of shortest path is there. So let's see one algorithm to show shortest path for a solution. This algorithm is applicable to undirected graphs and no negative weights. This is named as Dijkstra algorithm. This Dijkstra gentleman, he was from Netherlands. This is very similar to BFS. What is BFF? If this is our graph, like 3, BFS means we first come to here. No, here is not there. BFS first come here, then we will come to here, next this one, then we will come here, then we will come here. So BFS in breadth we search. Dijkstra is like BFS and weights are different because here we have weights. If all the weights are similar, then it is like BFS. The main objective of Dijkstra is if you have a graph and source vertex where we want to start, then our goal is to find the shortest path from that source to all vertices in a given graph. And the basic idea here is we maintain S like set of solved vertices, then at each step we select the closest vertex and we add it to S and realize all others from the U. Here is BFS. BFS very simple. First, we make some layers, right? Layer 0, layer 1, layer 2. First, we go to layer 0. We check the nodes. If there's no node, then we will come to the layer number 1. Then from here, we will go to this first node, second node, third node. Then we move to layer number 2. Then we go for the first node, second node, third node, and we will continue till where we see all the nodes. Here is the BFS algorithm. We have T like 3 consisting of only vertex V1, then L empty list for the visited one. We put V1 in L. Then while L is not empty, then we remove the vertex V from L and we go to the neighbors and we. So the idea is first we move horizontally and visit all the nodes and we move to the next layer. This is called as BFS. We have another one is DFS. DFS is like this. First we will come to this one, then this one, then this one. Then we will go back, then this one. Then here we will come back to here. Then here we will come back to here. This is called as DFS, differs. Dijkstra algorithm, so this is Dijkstra algorithm. It's a kind of iterative algorithm and it provides us with the shortest path, and we can start from one node, any node, to all other nodes to keep track of the total cost from the start node to the each destination, here we will make use of distance, like what can I say, we can weights. The distance instance variable will contain the current total weight of the smallest weight path from the start to the vertex in the question. Then, according to this loop, our algorithm iterates once for every vertex in the graph. However, the order that we iterate over the vertices is controlled by a priority queue. For example, we can say a set. The value that is used to specify the order of objects in priority queue is like distance, or maybe we can say some other weights that we have. So when a vertex is first created, distance is set to very large number, like infinity. When the algorithm finishes, the distance are set correctly as the procedure. So you can see here our algorithm. We have a graph. It's a kind of weighted connected graph, simple graph with all weighted positive. It means directed graph with no negative weights. Then here is our vertices like this, and length or weight as like this, right? First of all, we consider all as infinity, the weight from vi to vj that we are going to pass. So this is a for loop for I 1 to n. This is we consider initially as infinity. La is 0, S is 5. Then the labels are initialized so that the label of A is 0 and all other labels are infinity, because initially we don't know how much it is. Then as long as the set of our vertices is not in S, it means we iterate one by one. Then U is a vertex not in S, LU minimal, and we update our S as S union of U. Then for all vertices, V which is not in the S, we say that if L plus the weight is less than LV, then we update this one. And we repeat this one. Finally, it will give us the shortest path. So in other words, we first have a set which is our shortest path. And this one keep track of the vertices included in the shortest path. We assign a distance value to all vertices in input graph, and initially we consider all as infinity. We assign the distance value as 0 for source, because when we start, the distance is going to be 0. Then, while our S does not include all vertices, we pick up U, which is not there in S and has the minimum distance, and we put it into the S. Then we update distance value for all adjacent vertices of U. To update the distance values, we iterate through all adjacent vertices. And for every adjacent vertex, the sum of the distance value of U and weight of edge U to V is less than the distance value of F. Then we update the distance value of F. And finally, it gives us the shortest path. So here is one example of the Dijkstra algorithm. We will see how it works. As you can see here, we have 8 nodes, 0, 1, 2, 3, 4, 5, 6, 7, right? And we want to start from source, so this is our source. And this is our destination. As you can see here, there are some weight here, 7, 9, so these are considered as weights, right? Distance. We have one table here. This table is list of vertex. Noun means visited. If it is true, means visited. If it is false, means non-visited, right? Then this is cost or weight. And this is the path, right? So let's see how it works. Initially, the cost of 0 is 0 and the others are infinity. Then we check one by one. Once we visit one node, this one will be true. We change it from F to true, right? Then we will go to the children, and you can see node 5 is visited, right? Then we check the children, then we will go to 2 and it will be. So here, one by one, we check, and once we visit, we add it to our visited list. Then we will go for children and we will check and we will calculate the cost from the source to there. Then we will go to 5 is visited, and lastly 7. So 4 is remain. It means 4 is not visited yet. For 4 we can come to 1, 6 and 4, and so all are visited. Now we will go for path. From path we will add. From 1 is 0 to 1. From 2 is we came to 2 from 1 and we came to 1 from 0. So this is the path. For 3 we came to 1 from 1 and we came to 0 from 3. So to 1. For 4 we came to 6 and then from 1 then from 0. So you can see we add the path. For number 5 we came from 1 and before that we were in 0. For 6 we came from 1 and before that we were in 0. And for 7 we came from 6 and before that we were in 1 and we were in 0. So this is the path. So it gives us that 0, 3, 6 and 7. This is the possible path. Here is one example known as Traveling Salesman Problem. If there is a salesman who wants to sell something, suppose every morning he starts from one city and tries to visit several other cities and finally come back to his own city nighttime. We want to help him how to find the shortest path, then he can pay less transportation charge. This is somehow equivalent formulation for Hamilton cycle. The Hamilton cycle problem is to find whether there is a tour that visits every city exactly once. Every city, it means every node. Here, we know that the Hamilton tour exists because the graph is complete. And in fact, many such tours exist. The problem is to find the minimum weight. There are many solutions for this one because this problem is called as NP hard, right? NP hard means there is no polynomial time-known solution for this problem. The number of answers for NP hard problem have many space and dimension. And the number of solutions, when we have n as the number of city, then we can say it's 1 by 2 n minus 1 factorial. This is the number of solutions. For example, if you have 10 cities, then something like 181,400 ways are there. These problems can be solved using many algorithms like permutation, heuristic, genetics, simulated annealing, colony optimization, and many others. So I hope later in AI course, you will learn how to solve this problem. But here, this is a very simple way. Consider city 1 as the starting and ending point because he wants to come back to home. Then we generate n-1 factorial permutation of the cities. Then we calculate the cost for every permutation and we keep track of the minimum cost permutation. Then we return the permutation with the minimum cost. In this case, the complexity will be something like n factorial. And the last topic in this lecture is planar graphs. Now we want to study the question of whether a graph can be drawn in the plane without edge crossing or not. Consider the problem of joining three houses. So beyond to three houses we have, and they have different utilities like gas, water. We want to connect and we want to no cross between them. No cross between these three lines. Is it possible to join these houses and utilities so that none of connection cross each other? In this case, we have to go for graph planar. In this one, we say the graph is planar if G can be drawn in the plane with its edge intersecting only at vertices of the graph. Such a drawing graph is called as embedding of graph. We cannot draw planar graph in a way that edges cut each other. There are many applications like for VLSI design, circuit design, and many other things. So here is one example. If this is one graph, then we can convert it to this one because here we have cross, but if you change the direction from here to there, it's a kind of this one. In this way, it seems they can cross, but if we show it in planar representation, they do not cut each other. Okay, in this lecture, we learn graph theory, definitions, type, terminology, representation, subgraph, connectivity, Hamiltonian and Euler graph, shortest path problem, planar graphs, and we have many examples. I hope you understand, and please feel free to ask me if you have any questions. Thank you.